Hello, this is Huizhen Xue from UC Berkeley. Today I'm going to present our work about revisiting few-shot activity detection with class similarity control. This is joint work with collaborators from UC Berkeley, Boston University, and IIT Kerala, namely Ximeng Sun, Eric Zeng, Abi Das, Kate Sianko, and Trevor Dara. The rising popularity of video recording devices and social media has led to an explosion of available video data. However, the events are rare and require models to detect them based on owning a few training examples. In fully supervised activity detection, we have a predefined activity label space. However, in few-shot case, we don't have a predefined activity label space. The few-shot activity detection in real applications should be able to detect new out-of-list examples and generate reasonable predictions. So, what should an efficient few-shot activity detection model look like? It should be example-based activity detection. The classification should be based on similarities between few-shot activity representations and interested candidate segments in the video. We propose a few-shot proposal-based activity detection model in untrimmed video called FPAD. Here is a model overview. Our model proposes foreground action proposals and assigns labels to them based on their similarity to the one-shot or few-shot activity training examples. Additionally, we generate proposal features adapted to frame rate differences between proposal stream and untrimmed video stream. Next, I'm going to introduce our model in detail. Given an untrimmed test video shown in the top, and the few-shot training examples of several activity classes shown in the bottom. First, a 3D ConvNet feature extractor is applied to both the untrimmed input video and the few-shot trimmed videos to extract features. Then, a two-stage temper proposal subnet is going to regress temper proposals with predicted binary proposal scores. A similarity network is used to compute similarity scores between proposals and few-shot videos. Finally, the few-shot activity labels are assigned to the temper proposals based on similarity score. Next, I'm going to introduce our loss function. We design a distributional adaptation loss to supervise the feature learning for temper proposals and few-shot trimmed videos due to the potential frame rate differences in the two branches. Besides this loss, the total loss also contains the losses from the two proposal stages, LP1 and LP2, and the few-shot similarity network, LFS. Each of the proposal losses, LP1 and LP2, consists of a smooth L1 regression loss for proposal regression and a binary classification loss for binary proposal classification. The few-shot classification loss, LFS, in the few-shot similarity network is a multi-class cross-entropy loss. We also have a loss weight lambda to control the proportion of the distributional adaptation loss in the total loss. Next, I'm going to introduce the evaluation setup and evaluation metrics. We split the activity classes into non-overlap base and novel class split. We take the n-way k-short episode meta-learning. For evaluation metric, we take the mean AP and average mean AP, which are calculated in each episode for one untrimmed test video. And the final results are reported by averaging over 1,000 episodes. We experiment on 3 different datasets, ActiveNet 1.2, ActiveNet 1.3, and Tumors 14 datasets. For each dataset, we create 6 different base and novel splits considering the class overlap, namely random split 1, random split 2, random split 3, which denotes 3 random splits where there are no control on the possible overlap between pre-training classification classes and novel detection classes, and controlled random split 1, controlled random split 2, controlled random split 3, which denotes 3 controlled random splits with no overlap between pre-training classes and novel classes. Next, I'm going to present our experiment results. We first did some ablation studies on the hyperparameters. For example, the loss weight lambda for the distributional adaptation loss and the proposal score threshold. For the effect of adaptation loss weight, the detection results gradually increase and then decrease with the peak value at lambda equals 0.5. To show the effect of the proposal score threshold for our one-shot setting on the ActiveNet 1.2 dataset, we change the proposal score threshold between 0.1 and 0.5 with step 0.1. There is a trade-off between the quantity and the quality of proposals, and in this setting, the optimal proposal score threshold is 0.3. Then we report the one-shot results on different base and novel data splits. The yellow histogram shows the mean and standard deviation of 3 different runs on random split 1. From the yellow histogram, we can see that though there is certain randomness of sampling one-shot examples in each iteration, on the same data split, the mean AP at 0.5 results of 3 different runs are quite stable, with a small standard deviation. The green histogram shows the mean and standard deviation of 3 runs on 3 different random base and novel splits, without control on class overlap, namely random split 1, random split 2, and random split 3. The sign histogram shows a mean and standard deviation of 3 runs on 3 random base and novel splits, with no overlap between novel classes and classes in the SPOT1M classification model. The corresponding data splits are controlled random split 1, controlled random split 2, controlled random split 3. Comparing the green histogram with the sign histogram, we can observe that the mean AP at 0.5 decrease as novel classes become completely disjoint from the pre-training classes. The standard deviations on both sets of splits, the green histogram and the sign histogram, are relatively large. This may be caused by the internal class similarity between base classes and novel classes in the few-shot setting. We also report the result comparison of our one-shot and 5-shot models on 2 base and novel splits, random split 1 and controlled random split 1. for each dataset. Our model has relatively large improvement between one-shot and five-shot models over previous methods. Comparing our results on the uncontrolled split and controlled split, the relative improvement of five-shot on the controlled split is less, which means that when the novel detection classes and the pretending classes are totally disjoint, the relative improvement between one-shot and five-shot also decrease, but in general the performance is still good. We show one demo video with our one-shot and five-shot prediction from Tumors 14 dataset. Now it enters ground truth activity. Now our five-shot prediction and one-shot prediction. From the video, we can see that five-shot gives more accurate prediction compared to one-shot. In summary, we propose a few-shot activity detection model with an end-to-end trainable proposal network to detect potential events. We introduce a novel distributional adaptation loss to minimize the feature discrepancy across different frames. And we also evaluate our model on different base and novel splits of 3 activity detection datasets with different class overlaps, and demonstrate the effect of such overlap in few-shot activity detection performance. Finally, thank you for your listening.